In this video, we're going to see how to use limits to describe the behavior at a vertical asymptote. From the denominator, I know this graph is going to have a vertical asymptote at x equals -3. To think about what's happening around that vertical asymptote, we could try to make a sketch of the graph, or we could just try to think about what happens if I plug in numbers on the right side and on the left side that are getting closer to -3. So for example, if we put something like -2.9 into the formula, the top is going to be positive and the bottom is also going to be positive. And as I get closer to -3, that's not going to change as I get closer to -3 from the right. And so this second example, I guess I kind of jumped ahead. As we approach -3 from the right, the graph is going to climb toward positive infinity. To analyze what's happening from the left, I want to look at values a little bit to the left of -3, so -3.1. In that case, the top is still going to be positive, but the bottom is going to be negative. And so the graph overall is going to head toward -infinity. Since these two are not the same, since they're very different, and I could make a quick sketch of the graph to show that. On the right side we're going toward positive infinity, on the left side we're going toward -infinity, so it's best to say that this does not exist. In the second example, we can see that there is a vertical asymptote at x equals -2, and we can do a similar analysis. If I approach -2 from the left, if I think about what happens at values like -2.1, the top is going to be negative, and the bottom is going to be positive because of that square. And so the function overall is going to go toward -infinity. From the right side, if I think about what's happening for values that are slightly to the right of -2, the top is still going to be negative, and because of that square, the bottom is still going to be positive. So in this case, the limit also goes to -infinity, and we can say that the two-sided limit exists, I'm using air quotes right now, exists and goes to -infinity. So technically, this is a special way to say that the limit doesn't exist, but it doesn't exist in a way that sends it in the same direction, toward -infinity. And finally, I want to look at one more example. This example involves some factoring. We can factor the top. Two numbers that multiply to equal -2 and add to +1 are +2 and -1. And we can also factor the bottom. This is the difference of two squares. It factors as x plus 1 times x minus 1. And so before we think about where the vertical asymptotes are, it's really important to factor when we can, because in this case, notice that x minus 1 and x minus 1 cancels out. So the graph of this function is actually going to look very much like the graph of x plus 2 divided by x plus 1, with the important difference that there will be a hole in the graph at x equals 1. So this graph would not have a hole, but because the original formula included x minus 1 as a factor, the graph of this function does have a hole. So we have a hole at x equals 1, and we have a vertical asymptote at x equals -1. So thinking about what's happening at x equals 1, I've already said that there's a hole there. Well, where is the function headed to? The function is headed to wherever this function is going to go. So to think about the limit, we can evaluate the limit by thinking about that simpler expression, x plus 2 divided by x plus 1. If I plug in +1 to that, I get 3 over 2. And so the limit from the left is going to be 3 over 2 because there's no problem for plugging 1 into this formula. I can see that the limit from the left is 3 over 2. The limit from the right is 3 over 2. And the limit from both sides as we approach 1 is 3 over 2. And so we could say a little bit more carefully, right, the whole is at the point 1 comma 3 over 2. Now let's take a quick look at horizontal asymptotes with the 3 examples up above using these facts about horizontal asymptotes. If the degree of the numerator, if the degree of the top is larger, there is no horizontal asymptote. If the degree of the top is smaller than the degree of the bottom, we'll always get a horizontal asymptote of y equals 0. And if the degree is the same, we have to look at the ratio of the leading coefficients. So now we see in this first example that the degree of the top is larger, so there is no horizontal asymptote. In the second example, the degree of the denominator is bigger, the degree of the bottom is bigger, so there's a horizontal asymptote of y equals 0. And in the final example, the degrees are the same. It's not super interesting though. The leading coefficient is just 1 for both of those. So the horizontal asymptote is going to be y equals 1, the ratio of 1 over 1. In a separate video, I'll do sort of a complete analysis of one function. I hope you enjoyed this video. Thanks for watching.